This video covers differentiation for A-level pure maths, starting from first principles and building all the way up to finding the equation of a tangent line. We will follow a two-pass structure, a full worked process first, then a simplified recap at the end. Let's start with the big idea. The gradient of a curve at a point is not a fixed number like the gradient of a straight line. It changes from point to point, so we need a new way to find it. Picture a curve with 2 points on it, joined by a straight line called a chord. As we slide the second point closer and closer to the first, that chord's gradient gets closer and closer to the true gradient of the curve at that first point, the tangent gradient. Watch the chord shrink. As the gap between the 2 points shrinks towards zero, the chord rotates and settles onto the tangent line, the line that just touches the curve at that one point. This limiting process is the whole idea behind differentiation. This idea has a formal definition. F prime of x equals the limit, as h goes to 0, of open bracket f of x plus h minus f of x close bracket divided by h. Here, h is the small horizontal gap between our 2 points, and this whole expression is exactly the chord gradient as that gap shrinks to nothing. Let's apply this to a real function, f of x equals x squared. First we need f of x plus h, that's open bracket, x plus h close bracket squared. Expanding that bracket gives us x squared plus 2xh plus h squared. Now we substitute into the definition. F prime of x equals the limit, as h goes to 0, of x squared plus 2xh plus h squared minus x squared, all divided by h. The x squared and minus x squared cancel out, leaving the limit as h goes to 0 of 2xh plus h squared divided by h. Dividing every term by h gives the limit as h goes to 0 of 2x plus h. Now we let h go to 0 so that h term simply disappears. This gives us f prime of x equals 2x. That is the derivative of x squared, found entirely from first principles. Before we move on, here's a quick prediction for you. Using the same pattern you just saw, what do you think the derivative of x cubed will be? Pause for a moment and make a guess. There is a general shortcut called the power rule, so we don't have to repeat that limit process every time. It says derivative of x to the n equals n times x to the power of n minus 1. Check this against our x squared result. With n equals 2, the power rule gives 2 times x to the power of 2 minus 1, which is 2x. That matches exactly what we derived from first principles, so the power rule is consistent. And using this same rule, x cubed differentiates to 3x squared, matching the prediction you just made. Now let's differentiate a polynomial with several terms. F of x equals x cubed plus 2x squared minus 5x plus 7. The key rule is that we differentiate each term separately, one at a time. Term by term, x cubed becomes 3x squared, 2x squared becomes 4x minus 5x becomes minus 5, and the constant plus 7 differentiates to 0 because a constant has no gradient. Putting those together, f prime of x equals 3x squared plus 4x minus 5. That's the derivative of the whole polynomial. Next, let's find the gradient of this curve at a specific point, say where x equals 2. To do this, we substitute x equals 2 into the derivative f prime of x, not into the original function. Substituting gives f prime of 2 equals 3 times 2 squared plus 4 times 2 minus 5. Working through the arithmetic, that's 3 times 4 plus 8 minus 5, which equals 12 plus 8 minus 5, giving 15. So the gradient of the curve at x equals 2 is 15. Now, before we find the tangent line itself, here's another prediction for you. Which formula do you think we need to find the equation of a tangent line, given a gradient and a point? Think about it before the reveal. The formula we need is y minus y1 equals m times open bracket x minus x1 close bracket, where m is the gradient we just found, and x1, y1 is the known point on the curve. Let's use our example. At x equals 2, we need y1, so we substitute x equals 2 into the original function f of x equals x cubed plus 2x squared minus 5x plus 7. That gives y1 equals 2 cubed plus 2 times 2 squared minus 5 times 2 plus 7, which is 8 plus 8 minus 10 plus 7 equals 13. So our point is 2, 13. Now substitute the gradient, 15, and the point, 2, 13, into the tangent formula. Y minus 13 equals 15 times, open bracket, x minus 2, close bracket. Expanding the right-hand side gives y minus 13 equals 15x minus 30. Adding 13 to both sides, we get y equals 15x minus 17. That is the equation of the tangent line to the curve at x equals 2. Now let's pull everything together into one clear, ordered process. Step 1. Picture the chord between 2 points on the curve and imagine the second point sliding toward the first. Step 2. Write the first principle's definition. F prime of x equals the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. Step 3. Expand and simplify to find the derivative, or use the power rule n times x to the power of n minus 1 as a shortcut. Step 4. Differentiate a polynomial term by term. Step 5. To find a gradient at a point, substitute that x value into the derivative. Step 6. To find the tangent line, substitute the gradient and the point into y minus y1 equals m, open bracket, x minus x1, close bracket. Watch out for this common mistake. When finding the gradient at a point, students often substitute the x value into the original function instead of into the derivative. Always substitute into f prime of x for the gradient, and only use the original function to find the matching y value. Here is the simplified version, just the essentials. Gradient of a curve equals limit of chord gradient as the gap shrinks to 0. First principles, f prime of x equals limit as h goes to 0 of f of x plus h minus f of x over h. Power rule, x to the n differentiates to n, x to the power of n minus 1. Differentiate polynomials term by term. Substitute x into the derivative for gradient. Substitute the gradient and point into y minus y1 equals m, open bracket, x minus x1, close bracket, for the tangent line.